In the next few minutes, I'll show you what makes SSH different from TLS, why it doesn't use certificate authorities, what a host key actually is, what trust on first use means, and why the scary fingerprint warning matters, how public key authentication replaces passwords entirely, what the SSH agent does behind the scenes, and how a single SSH connection can become a tunnel that carries any other protocol, turning a remote shell into the Swiss Army knife of the Internet's infrastructure. Welcome to Defense Stack. We produce one concept a day, and each one stacks on the last, building the framework for security together. Let's dive into SSH. Last episode, we covered TLS, the protocol behind every padlock icon. TLS solves the trust problem by anchoring it in certificate authorities, third parties that vouch for which public keys belong to which domains. SSH solves almost the same problem, but it makes a different choice. There's no certificate authority. There's no browser-shipped list of trusted routes. Instead, the user, the human, or the automation running the SSH client is the trust anchor. That single design decision is what makes SSH feel different at every layer. SSH stands for Secure Shell. Its original job was exactly that, replacing the unencrypted telnet and RLogin protocols that the early internet used to open remote terminals. It's grown far beyond shells. The same encrypted session can carry file transfers, Git pushes, port forwards, and SOX proxies. Underneath, the cryptography looks a lot like TLS, Diffie-Hellman key exchange, symmetric ciphers in AAD modes, signatures during the handshake. But the authentication is where it diverges. SSH doesn't ask a CA whether the server is real. It just hands the client the server's public key and asks the client to decide. Now here's the question. Without a CA, how does the client decide whether to trust this host the very first time it ever connects? And why does that scary fingerprint warning we've all clicked through actually matter? It's a model called Trust on First Use, or TOFU. The first time you connect, the server presents its host key. The client has no way to know if that key is legitimate. It just shows you the fingerprint, a short hash of the key, and asks if you trust it. If you say yes, the key gets saved to a file called known hosts on your machine. From that moment on, every future connection to that host name must present the exact same key. If it doesn't, if a single byte of the public key has changed, SSH stops everything and shows you the loudest warning in the history of computing. That warning means one of two things. Either the server's been rebuilt and its key legitimately changed, or someone is sitting between you and the real server and you're about to hand them your shell. The protocol won't decide which one. That's why you're supposed to verify the fingerprint out of band the first time. Once host trust is established, the user has to authenticate. SSH supports passwords, but the right way is public key authentication. You generate a key pair on your machine, one private, one public. You copy the public half to the server into a file called authorized keys. From then on, login works like a signature challenge. The client offers its public key. The server checks authorized keys for a match. If it finds one, it sends back a random challenge. The client signs the challenge with its private key. The server verifies the signature with the matching public key. The private key never leaves the client, no password ever crosses the wire, and the server only ever sees a public key and a signature, neither of which is replayable. Phishing resistant by design. There's a usability problem. If your private key is encrypted with a passphrase, and it should be, you'd have to type that passphrase every single time you opened a new connection. So SSH ships with a small program called ssh-agent. The agent holds your decrypted key in memory after you unlock it once. Every SSH client on your machine then asks the agent, "Please sign this challenge," and the agent does it without ever exposing the key. Your private key stays encrypted on disk and decrypted only inside the agent's memory. When you log out, the agent forgets and the key is locked again. Agent forwarding extends this further. When you SSH into a jump host with the -A flag, your local agent becomes reachable from that jump host. So if you SSH from there into a third machine, the third machine's signature challenge gets forwarded all the way back to your laptop. Your private key never moves, but you can hop through several servers with one key pair. It's incredibly useful, and it has a sharp edge. Anyone with root on the jump host can ask your agent to sign anything they want, for as long as you're connected. They can authenticate as you to any server you have access to. The modern alternative is proxy jump, the -J flag, which gives you the same hop-through experience without exposing the agent socket on intermediate machines. If you remember one SSH best practice, use proxy jump, not agent forwarding. And once you have an authenticated, encrypted SSH session, you can write almost anything inside it. Local port forwarding lets you connect to local host on your machine and have the traffic come out on the remote side, useful when a database is firewalled and only the jump host can reach it. Remote forwarding does the opposite. It exposes something on your laptop to the remote server. And dynamic forwarding turns SSH into a full SOCKS proxy. Point your browser at it, and every byte exits through the remote network. This is how thousands of internal services are accessed safely from outside corporate networks every day. SSH is doing far more than carrying shells. In real-world infrastructure, this all comes together as a Bastion host pattern. A single hardened, monitored, audited server is the only machine on the network with port 22 open to the public internet. Every engineer, every CI runner, every deployment script connects there first, authenticates, and then uses proxy jump to reach the actual production servers behind it. It collapses the attack surface to one box. Logging, alerting, and key rotation only need to happen in one place. Compromise the Bastion, and you've compromised the fleet. But defending one machine well is a tractable problem. Defending hundreds isn't. Teams that take this seriously rotate host keys and user keys on a schedule, log every command run on the Bastion, and require a separate identity for every engineer. The Bastion is a single front door, but only if you actually treat it like one. Most applications in the world still ask users to type a password on a login form. That password gets sent over TLS to a web server, where TLS ends and a totally different problem begins. How does the server store that password so that even if its own database is stolen, the attacker can't log in as anyone? The naive answer is, just hash it. We talked about hashing back in episode 3. The naive answer turns out to be dangerously wrong, and the gap between hashing data and storing passwords is the next concept in the stack. That's the end of this concept, but each video stacks on the last. Subscribe and we add the next layer tomorrow. Up next, password storage. Why naive hashing is broken, what salts and key stretching actually buy you, and the modern algorithms, bcrypt and Argon 2, that an attacker with your entire database still can't crack. Thanks for watching.